Alrighty, here I am back with the 2022 Tauranga Girls College derived grade exam chemistry, and this is the organic paper. So I'm going to step through the naming of these. So we have to put either the name or draw them. So we have 1, 2, 3 carbons, so it's going to be a prop. This functional group is an amine, and that functional group is on carbon 2. So I would go 2-amino-propane. Or you could alternatively call that prop and 2-amine, either or. Okay, so this one here, we've got 2-methyl pentanoic acid, so we're going to start with 5 carbons. And the enoic acid is the carboxylic acid functional group, which I like to put on the right-hand side to make it easier. This now is carbon 1. So therefore the methyl group, meth meaning 1 carbon, has to come off carbon 2. So I'm just going to draw that as a CH3. And then I'm just going to complete this by drawing all my H's in. Note that I'm doing extended structural formula because I think that this leads to fewer errors. Okay, now we're on to this one here. So we've got, again, a 3 carbon main chain, which is a prop. We have 2 Cls. So if we have 2 of something, it's di. So this is going to be dichloro. And when we have a di, we need 2 numbers. So that's going to be 2, 2, 2. So we're going to have 2, 2, dichloro, and another propane. And the last one, which most people did well, we've got our longest carbon chain, which is a bute. So we've got 4 carbons, 2, 3, 4. Then we have 2 methyl groups, 1 on carbon 2 and 1 on carbon 3. So it doesn't matter whether you put them up or down. I'm just going to put them both down. And then we just need to make sure that we have all of our H's. Okay, boom, done. Okay, this one here, we did badly, and it was because of our reading skills, so we need to really read carefully. So we've got constitutional isomers, so that means everything's got to have 4 C's, H9s, and an OH group, usually. Yep. You may use the same isomer more than once, and you need to give a reason for your answers. So this one is a branch chain and a primary alcohol. So we've got 4 carbons. So the only way we can branch a chain is to go like that. Okay, it's 4 carbons with a branch. Some people did try to draw their 4 carbons with a branch like this. And of course, that is still just a straight chain bute, just drawn around the corner. So here's our branch chain. Our primary alcohol means that the carbon with the OH attached is only attached to 1 other carbon. So this one matches the description there. And I just need to complete it with the H's. It doesn't really say what you have to put for your reason here. So, I mean, the intention was that you had to give the reason for making that a primary, which is the carbon with the functional group OH attached is bonded to 1 other carbon. But really, you possibly could have put the reason for making it branch chain and the reason that it's a constitutional isomer somewhere. And some of you did all 3 of those things. Okay, on to the next one here. You just needed a tertiary alcohol. So we're looking for a tertiary alcohol with 4 carbons, and there's actually only one way to do that. And it's like that. Okay, I'm not going to draw the H's in the interest of time. So the carbon with the functional group attached is attached to 3 other carbons. Right, so that's what makes that tertiary. Do note that when you're putting an OH, the carbon needs to be bonded to the oxygen. Right, this one here needed to be an alcohol. So many people started not reading and giving me different functional groups. And it needs to be able to be oxidized to a carboxylic acid. The easiest one to do there is just your straight chain alcohol with all of its H's on. And the reason here, we needed to identify that primary alcohols get oxidized to carboxylic acid. And of course, the reason for that, I'm just going to write COOH here, is that carboxylic acids have to be on the end carbon, on carbon 1, so, and the functional group doesn't move, so therefore a primary alcohol has its functional group on the end carbon, and so does the carboxylic acid. This one here has to be a straight chain alcohol, so if we've got 4 carbons, it has to be straight chain, and it needs to be form one elimination product. Okay, so there are only 2 straight chain alcohols, so that's butane 1-ol, and the other one that we could have looked at was butane 2-ol. So we're looking for elimination products. So elimination is removing the OH and a hydrogen from an adjacent carbon. So this one will only have 1 elimination product. This one here, however, removing that OH, and you can either remove this hydrogen or this hydrogen from an adjacent carbon. So that is incorrect. That is butane 1-ol, and the reason needed to have that in it. Okay, so that was pretty quick. Over the page to part C. This is one of our long answer questions. So this one is comparing but1-ene and but2-ene, and they're reacting with H2O and H+. So one of the key ideas is that when we see a double bond, we're pretty sure that it's going to be an addition reaction. There is one other type of reaction that a double carbon-to-carbon double bond can undergo, and that is an oxidation. Starting redox now, so you know that oxidation requires KMnO4 or MnO4-. So this one's an addition. So again, we're looking at one of these reacting with H2O with a catalyst of H+, forming 2 products, and one of them forming 1 product. So we have to analyze these reactions. So when doing this, I'm sorry, that's my cat. Freddie, stop it. When doing any question in chemistry, I suggest that you start with the equations or the pictures. That will always help you. So if I start with but1-ene, and again, I'm not going to draw the H's in, but you must do that in your actual exam. And I'm going to add H2O with an acid catalyst. So an addition reaction, I'm going to break that carbon-carbon double bond. And if I break that carbon-carbon double bond, I'm just going to copy everything across, right? I open up 2 spots there for adding an H and an OH. Now looking here, if I add the H here and the OH here, I make butane 1-ol. But if I had have chosen to do it the other way round, I would have made butane 2-ol. Honestly, Freddie. Okay, so obviously this one here can make 2 products. Let's just check the other one out. So we've got but2-ene. Okay, plus H2O and H+. Again, we're going to break that double bond. And we're going to copy all the hydrogens across. Okay, so we've got 2 spaces now opened up for an H and an OH. So we have to look and see, are we going to add the H there and the OH there, or the H there and the OH there? And actually, whichever way we do it, we're making butane 2-ol. So there's only 1 product for that reactant there. Okay, so now we have to analyze it. So we have to meet all these bullet points, state the type of reaction. So that's going to be the word addition. And it says justify your choice, right? So we're going to justify it by explaining what addition is. So that's breaking, to be pretty careful with your language here, the C to C double bond, and adding 2 atoms or atom groups in its place. Oh, maybe we'll put 1 to each previously double bonded carbon. That's the best, probably the best definition, double bonded carbon. Okay, give the structural formula of all products, done. and identify major and minor. Okay, so the major and minor are up in this one here where we've got 2 products. So we have to come back here. So we're looking at this double bond here. C1 has 2 H's and C2 has 1 H. So this is the richer carbon. So for the major product, the richer carbon is going to get another hydrogen. So looking here, that hasn't got another hydrogen. This is the major here, right? So now we're going to label that major and label that minor. So we've done that, and explain how the major and minor products were identified. So that's what we're just going to do, what I just said there. We're going to put that into words. We're going to say in this original alkene, when we broke the double bond, the double bonded carbon that started with more hydrogens will get another hydrogen to form the major product. It hasn't actually asked you to state why this one forms 2 products and this one forms 1, but I think that's a clear implication in the question, and it says to analyse the reactions. So we would want to say that the difference between these two is that this is asymmetric, i.e. these 2 double bonded carbons are not the same as each other, whereas if we look at this one here, these 2 double bonded carbons are identical, so that's symmetrical. We should also say that we are adding an asymmetrical reagent, so we're adding an H and an OH. Okay, that's the end of question 1. Right, question 2, you are pretty likely to get a cis-trans isomer question. Okay, and it was a nice one, it was but-2-ene. So we're going to position our double bond in the middle, right? And we know there has to be a carbon-to-carbon double bond, and we know that each of these double bonded carbons has to have 2 different atoms or atom groups. So this one here is this one here, and this carbon here is this carbon here. So if you have a look at this carbon, it's got an H and a CH3. So I'm just going to put them there like that. And because I want the cis or the same side isomer, this carbon here has got an H and a CH3. So I'm just going to do like that. And then for the trans, I'm going to take one side and I'm going to turn it around like that. Okay, now elaborate on the features of but-2-ene that allow it to form geometric isomers. Just went through them. So number 1, we need to have a carbon-carbon double bond. So please don't just say double bond. You need to say carbon-carbon double bond. And we need to link this to the fact that this restricts rotation, not movement. Things can still move, but they cannot rotate, and fixes the atoms in place. Atoms in place. And the second requirement is that each, you have to word this carefully, double bonded carbon. It's not each carbon, each double bonded carbon must have 2 different atoms or atom groups attached. And just to get that excellence, we need to just link this to this molecule here. So I would say you can clearly see the carbon-carbon double bond. And if you look at this double bonded carbon, it has an H and a CH3. And this one also has an H and a CH3. So I would just write that into my answer. Each double bonded carbon has an H atom and a CH3 atom group. Boom, excellence. Really nailed this question. It's going to be in there, and it's it doesn't really change. Okay, we struggled with this a little bit, and this is quite tricky, so I'm just going to go through this one carefully. This is the old labels have fallen off the bottle question. They are 3 colourless liquids. So you've got an alcohol, an alkene, and you've got a carboxylic acid. And we need to use only potassium permanganate. And it's a solution, and that's a key word there. So some of you decided you'd choose your own reagents. You can't do that unless the question says choose your own reagents, right? So it's given us this, and that's all we've got. So we need to identify the liquids, and then we need to meet all of these requirements. So I'm going to add, there's nothing else to add, MnO4 minus / H plus. Just copied that from there. To a sample of all three. And we have to think about what we would see. Now, we should know that this is an oxidant and it oxidizes alcohols. Right, so that will react. This one is an oxidant and it also will do that funny reaction I just talked about with the double bond. So both of those two are going to react. This one, the acid, will not react with the permanganate. So we're going to write 2 samples will turn from purple to colourless. Some people wanted to say will turn purple. Well, if you imagine yourself doing this, you're adding the purple stuff to all three. They're all going to be purple because you've put the purple stuff in. What you want to know is once you've put that purple stuff in, does it react with this to go to colourless or does it not react with it to stay purple? Right, so we've got 2 samples will turn from purple to colourless. 1 will stay purple. And we're going to say that this is the carboxylic acid. So that's a negative reaction. It's actually propanoic acid, so I'll name that. Okay, we've got nothing else to add, right? If we had another reagent, we might take a second sample of the ethanol and the hexene, and we might add the second reagent to it. But we don't have a second reagent, so we have to look at this word solution. So solution tells us that it is in water, and we know that water is polar, and we know that polar things dissolve in polar water and non-polar things do not. So let's have a look at this. 2 carbons and a very electronegative O. So that's going to be polar. Over here, 1, 2, 3, 4, 5, 6 carbons. Nothing electronegative. That is going to be very non-polar. So we're going to look at the 2 that change from purple to colourless. Changed purple to colourless. One of them will form 2 layers and the other will form 1 layer. Okay, so ethanol is polar, so is soluble in polar water, therefore 1 layer is seen. Hex 1-ene is non-polar, so is insoluble in polar water, so 2 layers are seen. Okay, so that's our procedure. So now I know that the propanoic acid, when you add it to the permanganate, the purple will stay purple. These other 2, the purple will change to colourless, but the ethanol will form 1 layer and the hexene will form 2 layers. So I've got 3 different observations for the 3 of them. Right, have we done that? Yes, we have. Have we linked our observations? Yep, so the physical properties is the polar and non-polar. The chemical, so in that case, we probably need to say somewhere that a carbon double bond and an alcohol can both be oxidized. Right, so we want to talk about be oxidized. We want to talk about what the chemical properties are. And then we want chemical equations. So we've got 2 reactions. We've got ethanol, which looks like this. Again, I'm not going to draw my H's. We're going to put the MnO4 minus and H plus, and that's going to go to a carboxylic acid. Remember, in this standard oxidation is usually adding oxygen. Then we've got hex 1-ene, 3, 4, 5, 6. Okay, I'm just going to put my hydrogens all in there. And we're going to do the same reaction. This time we're going to break this double bond. 3, 4, 5, 6, and we're going to add the 2 OHs in. So I'm not going to put all the other H's in, sorry, but you see that I've broken that double bond and I've added 2 OHs in. You don't need to balance these. You're learning how to balance these when you do redox, but that is not required in organic. Okay, and over here, another distinguishing question. So you have to use something different, so you can't use permanganate. It does say a chemical test, so you really shouldn't use litmus here, although technically that is a chemical test. We have to distinguish between an alkene and a carboxylic acid. So your choices are, you could use bromine water, which is orange. You could use any metal. So let's say magnesium or zinc would be the best ones. You could use any carbonate, but most of you chose bromine water. So the bromine water is going to react very quickly with that double bond in an addition reaction, and it won't react with this, or it will react slowly with UV light and time. That one's tricky because, well, in fact, in this one, it doesn't actually ask you to write a reaction. It only asks you to identify the reagent, so you could have used bromine. State the observation, so we've got orange to colourless quickly, and over here we've got orange to colourless slowly or not at all. And the reaction type is addition and substitution. If you chose the metal or the carbonate, your observations would be fizzing with propanoic acid and no fizzing with this. And the reaction type would be, for this one, would be an acid-base reaction. Yeah, that's probably the best way to put it. Okay, over the page. Last question. Okay, this one was actually pretty well done. So people think you need to memorize all these, but you can work most of them out. So you're starting off with a carbon-carbon double bond. You know it's going to break into 2 new things are going to add. So what are the 2 new things? Well, it ain't platinum because we don't have a functional group with a platinum in it. That's just the catalyst. We can, however, break that double bond, copy the rest of the H's, 3 there, 1 there, and 2 there, and then add 2 hydrogens on. Right, straightforward there. This one here, we're going to put our 3 carbons in because that number of carbons is not going to change. We're going to copy everything. We're going to put those H's in. 1 H there, 2 H's there, 3, 1, and 2. So we've opened up these positions here. We're going to add an H and a Cl. So obviously one of them is going to have the Cl on carbon 2 and the other one's going to have the Cl on carbon 1. Does it matter? Yes, it does. Carry on here. Just look at this one. The functional group is on carbon 1. Therefore, the functional group must be on carbon 1 in this one here. Right, so this one must be the 2-chloro. Again, please put your H's on. I'm only missing them out in the interest of time. Okay, reagent X. So I'm changing a Cl for an OH. This is a pretty tricky one, but X is KOHAQ. That one you do just have to remember. That is a remembering one. And here we know that conc H2SO4 is a dehydrator. So we're going to remove an OH and an H from an adjacent carbon. And that is going to leave us with a double bond. Right, and this is an oxidant. So that's going to oxidize this. So we're going to stick with our 3 carbons. We're going to make a carboxylic acid. Just don't forget, once you've got a carboxylic acid, you don't have another hydrogen coming off this carbon. It's already got its 4 bonds. Okay, reagent X, we've done. Any special conditions? That's the AQ. Down here, the reaction type. So number 1, which is this one here. That's an addition. So we're adding through the double bond. Number 2, that's this one here. We are changing a Cl for an OH. So that's a substitution. Number 3, which is this one here. We are removing things in an elimination. And number 4, that's this one here. We are adding another oxygen in an oxidation. Okay, the polymerization, 3 repeat units of the polymer. So the key in here is we have to redraw our monomer like this. So there's our carbon-to-carbon double bond. This carbon has 2 H's off it. And this carbon here has an H and a CH3. Okay, and then we want to do lots and lots of those, but actually we only want to draw 3. So we're going to go copy 3 of those, like that, with the double bond broken. Copy the rest of everything through. So we've got an H and an H on the left-hand carbon, and an H and a CH3 on the right. Let's do that 3 times. Okay, and then we have to join them up, join, join, and then we have to show that there is a dot, dot, dot on each end. So some of you forgot the dot, dot, dot. Most of you actually had a good go at doing this, so that was really good. Okay, and I think this is the last question. No, it's not. Okay, so propane cannot undergo addition polymerization. Explain the differences in the structure and the reactivity of propane and propene. Right, so we need to define both of these terms. So addition is when we break the double bond between 2 carbons. And we now have 2 free points with which we can add something else on. And in this case, we are going to add monomers to our broken C to C bonds. Okay, and we need to always talk about polymerization as joining many, lots, millions of monomers, which are single units, and we need to do it to make a long chain. So we need to talk about that long chain macromolecule. Okay, so we've got addition, we've got polymerization. We know that propene has a C to C, which is reactive. Okay, and that's the key point. We know that the C single bond to C is not as reactive. And those are the key points that we needed in there. You can't say that this is a stronger bond than this. It is not actually. This is a stronger bond than this. However, this is a more reactive double bond. Right, so please don't talk about that being stronger. So reactive, less reactive, so we can join lots of these together, and we cannot join lots of those together. And that is all we need to write for that. And last question. This is a really tricky, nasty one. So we've got ethanamine, which is a base, and we've got propanoic acid, which is an acid. So essentially this is just a proton donation. Okay, so we will have this without its proton, CH3, CH2, COO minus, and this with the extra proton, CH3, CH2, NH3 plus. So really I think they wanted you to draw those both together. But actually, this is just a bit of a tricky question, really. So I wouldn't worry about that too much. And I'm just going to finish that off. The type of reaction is acid-base, and you need to talk about proton donation in that acid-base. And the last thing is the name, and that name is really bad. Like, honestly, ethan-ammonium. That's the positive one. Ethan-ammonium propanoate. Honestly, don't even bother about it. I think it's a stupid question. And I mean, every now and then they ask that in an NCA exam, but it really isn't a great organic question, and it will only be you'll be able to get an E8 without it, so don't fret. Okay, I've got to wind up because that's coming on half an hour. Boy, I'm trying to hurry, but it's taking me a while. Don't forget to look up the mark schedule to help yourself out, and don't forget, organic isn't as hard as you think it is. You can do it. See you soon.